So now you can see that, so this term, okay, here I'm focusing on the first term. The first term will become, okay, so this will be square root of d bar du. And the plus, the d bar square root of, and du. Then plus the 1/2, okay, the 1/2, and I want to make sure that, yeah, okay, so 1/2. Yeah, okay. Yeah. Okay, you see, here's a d log r, right?
Mm-hmm.
D log r. I'm going to put the d log r together with that 1/2. Okay. Then I'll move the square root r in front of this. Then I'll put the minus sign in front of it. So I'm going to do this one. So minus, then minus 1/2. So minus minus can become plus. Okay, then you have the d log r. Then the square root r, then d bar u equals 0. So I'll be able to reach to here, but however, the first two terms, actually it follows the product rule. Because here you can see that this one is actually d bar square root r and du, right? Du. Okay? So therefore, if you do such a replacement, and also you can remember this guy. This guy is defined to be the cube here. Defined to be cube, so this one is just the cube. Okay. Now, so therefore, if you read this, the equation will become this one. It's just the d bar square root r du, and the minus q to the square root r d bar u. Right. So that's the one equation followed from this one. And this equation is exactly the first equation here. Because v is equals to what? V is the du times square root r. That's good. So that's the v. Okay. And the other one is d bar u here is the w. Got a w. So therefore, you can see this equation separate. All right. Then if you change the order here, then you'll be able to do the other computation. Okay, so this one, you can see that from these equations, I will be able to get this system. So this is correct. So the next thing is how to go back. How to go back. Okay. How to go back, so again, it's involved some computation, but the basic idea is that you look at the transformation here. The transformation is use the d du, d and d by u, right? They multiply by r to get this. So that's the VW, the solution to the system. So how do you go back? So you want to go back from VW to a single function u. Now how do you determine the functions? So what you do is you replace this guy to here. I mean, once you have a solution VW, you multiply square root r. Okay? Now this square root r, the r is related in the system in Q, right? Q is equal to certain things. Now once you put here, so you're supposed to get the du and d by u. Now how do you show that this pair of vector, this pair of scalar function will correspond to potential u? How to do that? Now suppose that it is a potential. Okay, so let's do experiments here. Okay, suppose du is equals to, okay. supposed to be equal to. This is something we will expect, right? If we want to go back. Okay, so d bar u is equals to r negative 1/2 in W. Okay. So if such a u exists, okay, then this u, sometimes you can call it potentials. So this potential u will pose some conditions on this two vector, on this scalar function. Why? Because d bar du is equals to d bar u, right? So if you differentiate this in d bar, you are getting this one. And if you differentiate this in d, you'll get d r negative 1/2 W. So this two things has to be equal. Now, that means if the u exists, then you will automatically have that. But there is a result in complex analysis of multidimensional calculus. We say that, easily prove that this is compatibility condition for the existence of that potential. So I mean, we're going to prove that. Once this is proven, then we can show that there must be a potential u will give you this. Okay, so once this is known, then you can plug it into the system. That system will automatically go back to the questions. So first things we want to prove this, right? Now in order to prove this, we're going to give some E notation we call this E, for instance. This is F, for instance. Okay? So we need to show that D bar E is equal to D F. That's the thing we want to do. So what we're trying to do is that we only do one piece here. So I'm going to compute d bar e equal to something. Okay? I use the equation, and then I'm going to do a similar computation for df. Then I skip some detail, but actually end up you landed to the same thing. So therefore you have that. Okay. So dE first. So d bar e, so this is d bar, then you put the r to the negative 1/2 to the b, right? So b is equal to, e is defined that way. Okay? So now we want to compute it using the equations system. So I will multiply this out. Now what is d bar b here? What is d bar b?
QW.
D bar b, the system which is d bar b is
QW.
It's QW, right? So therefore I can rewrite this as d bar negative 1/2 b plus 1/2 QW. And the Q is equal to that. Now I'm going to plug all this information into this expression to see this end of this one. So you can see that d bar e is supposed to be something related to the E and the W, some combinations, right? So this is now the rest of the combination is just straightforward. So you do this, it's negative 1/2, then r to the negative 1/3, is 3/2, and d bar r. And it comes b. So this is the coefficient of b. Then plus the r negative 1/2, and the q. Now what is q? Q is equal to negative 1/2, then d log is equal to d log r. D log r is to dr, then dr. Then you have the w, right? Okay, so then you can see that this will have. So you can eliminate this r in the denominator. Okay, eliminate that, you replace it by square. So you have. Okay, and then you have a negative 1/2 just like here, negative 1/2. So therefore you can move out this common term, negative 1/2 r, negative 3/2. Then you have this d bar rb plus dr and w. Okay, so you have this. So you can see that d bar e is equal to that. Okay, then you do the same thing for the df. So df is d and negative 1/2 and w. So again, you do the same computation. You put d of negative 1/2 w, then plus r to the negative 1/2 dw. So d equals d r negative 1/2 w plus r 1/2 then q bar to the d, right? Q bar to the d. Okay. Again, that's the second equation in the system. So again, this equals negative 1/2 r to the negative 3/2. And so here we're differentiating this and dr and w. Okay, the plus r negative 1/2. The q is equal to negative 1/2 and the d log. So that's the d bar log. Q equal. Yeah, I mean, now r is a real function, so if you take the bar of q, meaning that you replace d by d bar, that's it, right? So this gives the d bar, r, the bar, and the d. Okay, then you check the detail here. You can see that here, again, this r cancel with here, we have. Okay, so you can move this. So this one equals to you replace 1/2 out. So 1/2 r negative 3/2. Then you have the d r w plus d bar r d. Okay. So this one is the same as this. No difference. No difference. So from here you can see that we verify that the compatibility condition here. So this compatibility condition tells us that DE equals to DF. So this compatibility condition shows that there is a potential sign, so that E is equals to DU and F is equals to D bar U. Okay, there is a potential function set like that. Okay, so this implies that. So now we're going back to the equations. So this shows that here we keep track of the so we want to recover BW first, right? Okay, so what we're trying to do is that we multiply R back to here. So you can see, now you can see that the D is equal to square root of R du, and W is equal to square root of R du bar. Okay? You get that. So previously, BW is just a pair of scale function. And now we show that this pair of scale function corresponds to potential related in this way. Okay, so then we're going to, the next step, we're plugging this things back into the system. So where is the system? The system is here. I'm going to plug it back into the first part. Okay. plugging back in the first part, you can see that this is just the, so the first is a d bar square root r du, okay? And so this should equals to q to the w. W is equals to square root r d bar. Okay. And so I'll plug in to the first one. And the first one is automatically will give you the scalar. I mean, will give you the previous conductivity equations. Okay, because you can multiply, compute this really fast. So you get square root r d bar du plus the d bar square root r and du. Okay, equals to q. Now what is q? Again, q is negative 1/2. Negative 1/2. And the r, then the r, right? Then equals square root r. Okay? And then you can see that this square root r, okay, removed, so this was for the square. And then you can see that this expression is basically equals to negative d square root r, and d bar, right? Yeah, okay. Here we have to recall the previous when we work out the forward way, what we define as a sigma. Sigma is equals to log r. Right? Equals to log r. Okay. Okay. So I'm not going to just leave this alone. Leave this alone. Okay. Okay, so now I'm going to walk this turn to the right side. Okay, so here I still want to work out this one. So this one is equals to 1/2 dr d bar r square root r. Okay. And the key is this carries the same similar feature. Then I'm going to move this turn to the left side to kill that minus sign, the plus, and make it this 0. And then I'm going to divide the square root r on both sides. Okay, if I divide this, then this term, which is equal to that, then you no longer have the square root r, right? Like this. And here, if you divide square root r to here, you also remove the square root r like this. And then you can see that this thing is just Laplace u of d bar du plus the 1/2. So you have a 1/2 in common, so for the magnitude here. Then this thing is just d bar sigma. The sigma is log r. So this expression is basically the d bar derivative of sigma. Okay. Then times du. Then plus, here is the d sigma, d bar u. So you can see that from here, this equation, okay, from here you're getting this equation. This equation now reduced to this equation. Now if you turn the page, go back to the previous reduction. In that direction, we remember there is an important middle step. That important middle step say that this conductivity equation is equivalent to this equation. and this is what we get here. So once I get here, because this equation is equivalent to this one. So therefore, you go this direction, finishing the other side of the go back part. Okay? Because one side, you see from the system here, once I verify this compatibility condition, then I have some here, then these two equations basically equivalent, there's no difference. You take bar for the first equation or the second equation. So this is our reduction directly. So this reduction shows that this is valid. This is valid. Okay, so, but however, this is just the proof of equivalent between the equation and the first order system. But the key is what we should do with the system. What we can do with it. And associated with the conductivity equation, you have the lambda, right? That's the derivative. The division, right? So that's the data of our inverse problem. That means I know this, how do I determine R? Okay. So now the question, our unknown function in the system is the Q. Now if I can recover the Q equal that, of course I can recover R, no problems. Right? But the thing is, this equation reduced to that. Now what is this reduced to Newman mapping is reduced to what? Because the system carries no boundary value problems. The boundary value of the solution here is not arbitrary. They're reciprocal. Okay. So therefore, what we can say, how this is reduced to what? If this is in here, what we're trying to do is we're going to define a new thing called a Cauchy set. It's a CQ. Q is dependent on here. It's equals to F1 equals to all the pairs, the boundary function, such that F1. So this means that there exist solutions. VW such that V on the boundary equals F1 and W on the boundary F2. You see, as I said before, so if you look at this complex system, once you have a solution, the boundary value here, F1 and F2, are not arbitrary. In the equation case, the boundary value is arbitrary. I mean, you can post any boundary value to get a solution, right? To get a solution, because it's second order, the reason. But however, this is first order, so the boundary value is not arbitrary. Okay. So if I collect all the boundary value, so this is only a subset. You can consider this only a subset in certain function space. Okay. But this subset will carry some information. It turns out that this subset can be determined by the distribution. So from here, I can recover this. Okay. So then we're trying to show that these things can be used to recover Q. Then from the Q, I can recover R. So that's our basic idea. So the next thing we want to prove is that why the distribution map can be used to recover the CQ. Why this lambda R is determining the CQ. So that's the next thing. But the proof is not difficult, actually. So do we want to continue from here, or we can continue next time? Because we have very complicated today. You want to learn more? Okay, let's go. Okay, so first, you see the disk in your map, okay? So let's say you have the conductivity, carry the same disk in your map. So then you can, from here, the boundary determination will tell you that based on the boundary should be right. So here, we assume this is like a C2 functions, okay, C2 functions. So this one, and also, and the gradient, 1 on boundary, equals gradient, 2 on boundary. So I'm going to have that first. Okay. Now suppose I have a pair F1, F2, okay, belongs to CQ1. Okay, so our goal is trying to show that we want to show that the CQ1 is equals to CQ2. So that's the thing we want to look for, right? Now suppose I pick up, so this is our, because under this assumption, we want to show CQ1 equals CQ2. But this assumption itself implies the boundary determination, so this is something I already know. Okay, the second step, what we're trying to show that the CQ1 equals CQ2. Now how do you show CQ1 equals CQ2? We remember set theory, right?
Yeah.
We remember, so how do you prove A